Hi, I'm Oliver Gao. I'm the director of Cornell System Engineering Program. Today, we're so delighted to have Professor Dinesh Verma, who is the executive director of the System Engineering Research Center, which also known as SERC, which is the first university affiliated research center established by the DoD for system engineering research.
It's a real great pleasure to be here and to meet you, Oliver.
Oh, thank you. So, I was looking at your development. I think kind of you got your bachelor's degree from mechanical engineering, and then you move on to get your degrees in industry and systems engineering. So, it looking back, it was really, I think, such a wonderful career. Like you worked both in industry and then also in academia.
Yes.
So I think me myself, and also I believe a lot of us who will be watching this video, we are very interested in knowing, if you look back, how your career started and how your career developed and brought you to this point.
So I finished my degree in mechanical engineering, and then I worked in industry for a year in the area of thermal and hydro insulation using fiberglass products. Came to the US to Virginia Tech for my graduate degrees. I got my master's and my PhD from Virginia Tech, as you said, in industrial and systems engineering. My focus on systems engineering became sharp as a result of my two advisors, Ben Blanchard and Walt Fabrici. They were the ones that encouraged me to focus on this area, and I quite enjoyed it. And towards the end of my PhD program, when I was about to graduate, there was a systems engineering conference, I believe in Minneapolis. And I made a list of about 8 or 10 mentors, half of them who were senior professors and half of them who were senior in industry and government. And I requested all 10 of them for some time for some advice and counsel at this conference. And to my surprise, all 10 suggested to me that if I wanted to become a high impact faculty member in systems, that I needed to first have experience in the real world, working with systems. And so I always knew I wanted to join academia, but I decided that I will put that on hold and get some good experience working with an industry and with the government on real projects, building real systems. And I was fortunate enough to get an appointment at Lockheed Martin Undersea Systems. And so I worked on systems that are basically being developed within this part of Lockheed Martin for the US Navy. I did that for almost 8 or 9 years. And towards the end of my time at Lockheed Martin, I had an opportunity to rejoin academia, and I joined Stevens Institute as a faculty member in September of 2001. So I've been there since 2001.
And I probably not too long after you joined that, and then you started the SERC.
I joined Stevens in 2001. We competed to have the opportunity to establish the SERC at Stevens in 2008. So I was at Stevens for almost 7 years before the competition for the SERC happened.
I see.
It was in 2007 that the then president of Stevens, the provost at Stevens, and the board of trustees took a big risk in establishing a brand new school of systems and enterprises. And I became the dean of that school in March of 2007.
It's interesting. So why did you say that the university took a risk?
Because it was the only school of its type.
That's true.
Yeah.
That's true.
And
yeah.
so I think they were driven by their conviction that systems would become increasingly important. A systems point of view, underpinned with appropriate science, would become an increasingly relevant area of research and education. But I say risk because nothing is guaranteed when you begin a new initiative.
That's true. Yeah, that's true.
And so it was launched in 2007, and fortunately, if you know how academia works, these things can only grow if they're nurtured by the senior leaders within an academic enterprise. And we have had that support over the years, which is why I think the school is what it is. We now have a brand new dean who was appointed about 3 months ago, Yahia Masood. And of course, the SERC is almost 10 years old now, and we're in the process of going through our second renewal for the third 5-year term.
So Dinesh, I think you mentioned, this School of System Engineering and Enterprise, right? So, and this reminds me kind of, the history of this Cornell System Engineering. It's a program.
Yes.
It's not an individual department.
Yeah.
However, the structure it's set up that actually we draw faculty from all the different departments.
Yes.
So the program so far, and we call the College of Engineering Systems Engineering Program.
Yes.
So it's underneath College of Engineering.
Yes.
So, for example, when we think about the future of this program, of course, you can see a lot of people think, okay, you start as a program, like your goal could be we want to grow into a department or a school. But I was thinking about that, and probably I would like to consult you about this thing. So the nature of system engineering is that, and also the power is that we draw knowledge and intellectual power across different departments, and we all know that in the traditional academic, like university environment, when we have departments or even kind of individual faculties within a department, a lot of times they become their own silos.
Yes.
Right. So actually, we feel that in a system program cutting across all the different departments. So like kind of this program, we draw faculty from civil and environmental engineering, from ORRE, and from mechanical engineering, from ECE, and also Cornell has this graduate field structure. We draw faculty from all over.
That's an impressive concept.
Yeah, all over the campus.
Yes.
So I was just afraid that okay, if one day this program grows into a department, and all in a sudden, it becomes its own silo.
Yeah.
Instead of functioning as like a cement or conglomeration. So what did you observe, like kind of when Stevens started this school, and how is this school now interacting not only within itself but also across other because I think if it's a school, like some research, I was impressed that in your SERC research you also mentioned these human factors. Like humans, social scientists are not necessarily within the College of Engineering.
Yes.
So how do you still cultivate this cross-disciplinary?
I think you're correct. I think the different universities, driven by their organic constraints and degrees of freedom, have found different models for supporting and nurturing interdisciplinary research in general.
That's true.
Systems being one such area. I don't think there is a dominant model. I think different universities try different things with varying levels of success. For a variety of reasons within a school as small as Stevens, this was the path we chose. Now, as it is with any path, one can look back and think about how we could have done things maybe a bit differently, maybe even better. Certainly within our school, we have faculty members with very diverse backgrounds.
That's nice.
We have faculty members with advanced degrees in mechanical engineering and electrical engineering and computer science and operations research, systems engineering, actuarial science, statistics, mathematics. And so we do have diverse faculty within the school. We have also made nice internal bridges with the other schools. And I think that's an area where we can do a lot more. And I would say, along with those internal bridges, we've also created external bridges. The external bridges that we've created, I think we've done rather well. And when I say external bridges, I mean collaborative agreements with our peers within academia, certainly our supporters, collaborators, and sponsors within industry and government, not only with regard to research but also with regard to education. We had a explicit focus on building external bridges. During my term as dean, I think I would give myself a good grade for the external bridges. I wish we could have built better internal bridges, but I think we are focused on that increasingly now. But you're right. I also think that whichever model any institution uses, it requires energy and caretaking to make sure it works. It needs a champion and it needs support and an appropriate incentive structure. So, we all have, every university has found its own way to do it. We just found our way. And in many ways, it's been rather good. And in some ways, I think we recognize we need to strengthen it.
So from your point of view, you've been very well connected to all the world-class researchers and thinkers in systems. So where do you see systems engineering or system science as a discipline? Or are we a discipline yet? And where this discipline or this research community should be heading in the coming years?
I think there is increasing convergence about the enabling disciplines that supports the practice-oriented field of systems engineering. Whether it's decision sciences, decision theory, cognitive science, complexity theory, there's many fields of research and variety of disciplines that support and underpin systems engineering.
Pillars.
That's right.
Yeah.
Certainly including operations research, as is the case at Cornell. My view is that it has always been the case in the past, but I think it's becoming very explicit now, where we truly are thinking of systems at societal levels, where the engineering and technology components of the system are strong, but they're only a small part of the overarching system. We now have some really great faculty members who are looking at not just the physical sciences, but the social sciences and the blending of the two. We're looking at societal systems like healthcare, financial systems, even things such as cybersecurity, transportation systems, where you have such a lot of interest, where certainly they're all technology and engineering enabled, but they depend so much on good policy. They depend so much on good regulations. Our ability to do modeling to understand good policy from bad policy, not just in terms of the short term, but also in terms of the long term. So I think this notion of socio-technical systems at scale, where these socio-technical systems are distributed with distributed governance, that notion of the extended enterprise is where a lot of really exciting research is happening and will continue to happen. Secondly, I think if I was to become more parochial towards engineered systems, which are largely dominated by engineering and science, and certainly increasingly, more and more user-centered in their synthesis, I think this notion of using computational resources to traverse the design space, which is becoming increasingly, has increasingly higher levels of dimensions. So, if I look at the design space, we have more and more variables getting added to it. We never thought of security the way we think of security today, as an example. And so this notion of an n-dimensional design space and our ability to traverse through that design space, not in a sequential manner, but using computational methods to look at a lot of things in parallel, that hopefully will allow us to compress the design cycles. So there's a lot of, I think, interest in using computational methods to enhance our design synthesis, design analysis processes, certainly looking at socio-technical systems at the scale of, at societal scales. I think there is another issue, particularly in economies which are advanced economies, mature economies such as the United States, where there is a tremendous amount of domain knowledge that is in danger of getting lost unless we figure out a way to capture it for the benefit of future generations. That is another concern that is, I think, driving a lot of investments within industry and government today. So that's kind of my sense for where. And of course, how can you ignore the idea that, it used to be that most of the research in systems engineering came from the national security ecosystem. That is not necessarily true today because we're designing highly complex systems in non-defense sectors, such as automotive. And so if you look at the use cases for an automobile, they're way more varied and diverse than a set of use cases for a fighter airplane. And so, organizations in the private sector are dealing with complexities that certainly challenge complexities that we're dealing with in the national security space. In that sense, it's kind of exciting because you've got a lot of interest in this notion of highly complex, evolving socio-technical systems. Certainly with advances in machine learning, artificial intelligence, development of new control regimes for hybrid man-machine collaboration in tactical situations and strategic situations and various dimensions which are often driven by the application domain itself. I think that's going to be, I would say this is a period of renaissance in systems engineering research.
One point you mentioned, this kind of, even the cars versus airplanes. Like, of course, kind of seemingly, airplanes are much more complicated than cars, right? However, just look at this kind of recent example of this Uber driverless car hitting a person, right? Airplanes probably mechanically more complex. However, airplanes are flying in the air. There's no person airplane could hit it. However, not because of this involvement of human factors. Actually, a Uber car and Uber driverless car could be way more complicated.
Certainly, the number of scenarios you have to contend with is likely to be a lot more difficult and diverse in quite a few non-defense systems.
The commercial systems. So you also, I think, kind of mentioned, like now with this autonomous, AI, artificial intelligence, machine learning, right? It's really exciting, right? So, but in the meantime, you mentioned that there is a danger for the loss of the domain knowledge. So on one hand, right, we are even talking about like human brain connected to computers that we want. So, and versus this kind of loss of domain knowledge, how do you see these two things?
Well, we talk about developing new systems without realizing that so much of what we have today will be with us for the next 20 years, if not more. Mm-hmm. So much of what we depend on is legacy systems that does not have artificial intelligence, is not instrumented for data analytics, is built on architectures and certainly software and hardware partitioning concepts that are not very well documented. Often we know what the design is in these legacy systems and we don't know why it is the way it is. And so when we don't know the design rationale of existing systems, we may, while trying to improve a system, in fact, have the opposite effect. And so I think it's exciting for us to be thinking of systems of today and the future, but we cannot forget the systems of the past that continue to support us. And so legacy is going to be with us for a long, long time. And I think some of the fear is that we ought not to lose the domain knowledge that helps us understand that legacy that we will be depending on for the next 20, 30, 40 years.
This reminds me when I was reading your work, like your earlier work, but kind of this maintainability, supportability, and also life cycle.
Yeah.
This legacy system, how can we incorporate this kind of the previous history of a legacy system into a life cycle, like management optimization?
Well, there's a lot of people that are obviously doing that rather successfully, where every time, anytime you have to do significant upgrade to the system, it's an opportunity to upgrade the system, modernize it, and make some improvements to it that align it better with regard to your strategy for those systems in the future. But at the same time, I think there is a danger that if we know the design of the system, but we don't know why the system is designed that way, if we don't know the design rationale, we might make certain assumptions that take our degrees of freedom away when we think about restructuring those systems or creating evolutionary systems in the future. I think it's important for us. I actually just fundamentally believe that our ability to build better systems in the future will, to some extent, depend on how well we understand the history of that system.
So in our this speaker series, so we also had historians come to talk. I think one historian was talking about the Vietnam War, and I remember when I introduced him, I said that we think about system engineers. We all think about this kind of specific physical system we build and look at. However, I think, and you mentioned history again. Historians are actually system engineers, like examining into how human society evolve.
Well, certainly knowing the context of what makes the system the way it is today. What were the constraint sets that folks 30 years ago dealt with that caused the system to be the way it is important insight as we go about trying to improve that system.
What kind of intellectual power should we equip the future generations of system researchers from a research and also education point of view, and in the context of what you just described?
Again, the way we fundamentally, I happen to believe that systems programs will continue to evolve. I think if I look at our own program at Stevens, we began with what you would think of as classical systems engineering courses, courses that would focus on understanding the stakeholders and requirements and building architectures and integrating systems and managing the whole process. And then we later on evolved into courses that were more built around various kinds of methods for modeling and simulation, analytics. Since then, we've continued to add courses in dynamic modeling, complexity theory, systems thinking, modeling and visualizing complex phenomenon, decision making. I suspect we'll continue on that path where we will probably have courses conjoined with departments such as computer science, certainly history, humanities, that's right, social sciences. So in that sense, I think to your point, I don't know that all the courses in future that support an individual's education in systems science and systems engineering will necessarily come from a single academic entity.
this program started as a Master of Engineering program. Actually, we work very closely with Lockheed Martin because Lockheed Martin has a system integration division in Owego,
Yes.
about 30 miles from
Yes.
here. We started that. But I think and we're doing the same thing in addition to cover the traditional system engineering field. The Cornell program trying to focus on the commercial systems.
Yes.
So about 5 years ago, actually, we started. So before it was just a Master of Engineering degree program,
Yeah.
but 5 years ago, and we started effort to build a research arm.
Yes.
So that's actually how we started this speaker series to bring people like
Yes.
you, these world-renowned speakers, to expose ourselves to the frontier of this research. And then 2 years ago, our proposal for a PhD program was approved by the New York State Education
Okay.
Department.
Congratulations.
So one thing is I just want to share with you, when we start this PhD, we call PhD in systems. We drop the word engineering.
Yes.
So we say PhD in systems. That way, actually, we are open to, as you say, any person,
Yes.
kind of as long as they have, a very good, grasp of the systems view, and they want.
Well, that's the reason why our school is called the School of Systems and Enterprises.
That's right, and I really like you also have the enterprises, because my personal understanding is that for any program, right, of course we want to educate future generations of researchers and the workforce, but we want them to impact the society, to contribute to to the real world.
Yes.
So in that sense, I feel like the word enterprise is really linking, right?
All the different dimensions.
different dimensions.
The technical, the engineering, the social, the political, the economic. Agree.
Yeah, that's right.
Yeah.
So we last fall in 2017, we welcomed our first cohort. Of the PhD, we had about 12 PhD students in the first
Okay.
cohort.
Okay.
We started, and we had students who had background in psychology
Yes.
and who had background even in philosophy,
Yeah.
and coming to this program.
Very nice.
In systems.
Very nice.
So, of course, speaking of that, in it seems you have had both undergraduate, master's, and also PhD in systems.
We don't have an undergraduate program.
Oh, you don't have?
No,
I
it's
see.
only master's and PhD.
Master, PhD.
Yeah.
So
We have an undergraduate minor in systems engineering,
I
but
see.
we don't have a degree at the undergraduate level in systems engineering.
I see. So now, looking at your master degree and PhD degree, what is your vision for? Of course, these two degrees they serve two different purposes, but what is your in your mind the division or the difference between these two levels of the system program, and also your expectation and mission?
Well, certainly, probably no different than at any university. I think at the master's level, it's more about knowledge dissemination and knowledge application. And at the PhD level, it's about knowledge development. And I think we're holding true to that. While we have hundreds of master's students, we have very few PhD students. I think every year we have numbers that are similar to yours. We graduate about 6 to 10 PhD students every year
I see.
from systems. That has remained in that range for the last few years. I don't think it's going to change too much over the next few years.
I
you know.
see.
Yeah.
Yeah. So.
And I would say our graduates end up with diverse careers. Some of them become faculty members. Some of them join industry. Some of them remain in government.
Mhm.
So, yeah.
Cornell, we submitted our application to become a member of SERC. And after we have made effort for many years, but I know that there was no opening, right? So, do you want to talk more about SERC? Because I think it's such a nice platform. It's not only a platform, of course, there is funding from DoD, and it's really such a nice consortium, right? For system research. Do you want to talk more about SERC?
So I would say there is a formal set of deliverables we have, and then we have, I think, some informal deliverables as a result of the SERC. I think I agree with you. I think SERC is a unique research center. It's certainly a unique university-affiliated research center. I think it has always had an intent to crystallize a network of research faculty doing work in systems-related areas. I think that was an aspiration at the time the SERC was established. I think most people would agree that we have created a non-trivial network of faculty members across the 22 universities that are currently members of the SERC. That was never a explicit deliverable, but that had always been the intent of all of us who have been involved with the SERC to really think of the SERC as a distributed center with multiple nodes of excellence across the 22 universities. I would say that the encouragement and even direction that we've received from our sponsors has been consistent, that they want this to be a network. And with that, they get diversity of thoughts, diversity of skills, depth of skills. We can leverage faculty members from every and any branch of engineering, science, or social science, or humanities for that matter, as a function of the research topic that is being considered. So I think it gives the government a lot of flexibility, and it allows us to build a community that is cohesive. Having said that, the SERC has also contributed in very tangible ways to the field. One example is Bookcase. Bookcase was initially sponsored by the Department of Defense as a project to build a body of knowledge for systems engineering. And along with that project, the faculty members who were involved with that project developed a reference curriculum for systems engineering. Bookcase today gets approximately 30,000 unique visitors to its website every month.
30,000.
30,000. Greater than 30,000.
Mm-hmm.
It is probably the most popular systems engineering related website in the world. And it has brought a tremendous amount of consistency within academia with regard to some of the core topics and core courses that are taught at the graduate level anywhere in the world. So yes, I think the SERC has had a huge impact on the maturing of systems engineering and the building of, certainly in the US and then beyond.
I think that's true. That's actually kind of, for discipline to be developed, and you need a community.
That's right.
And the community requires a network.
That's right.
And a network requires a platform, right? I think it's really that's otherwise kind of you could have twice as many people who are interested in systems. However, if they're not
brought together in some cohesive fashion, that is right.
That's
right. And I would say that through the SERC and the faculty leaders we've had within the SERC, we've been able to influence some of the technical societies. And I would say in that regard, there has been quite a convergence within the field in important ways, so that we can, to your point, I think we have a core platform that we can together build upon. So I would say that was never articulated explicitly as a deliverable, but that has been a deliverable of the SERC to the community. That's right.
Yeah, I think probably kind of that, that's probably a much bigger deliverable than what you deliver to DoD.
That's right.
Right.
That's
so because,
right.
to the society.
That's right.
Yeah. So speaking of that, so the development of any discipline, right? Kind of, so that's what I call like an infrastructure. You build this, this infrastructure, right? But for the discipline, for the community to move forward, especially now with today's system challenge, as you mentioned, we are in the period that you use the word renaissance, or
Yes.
right in this period of time. So for this, while we have, if we think of this as either as a pyramid structure or something, or even, so what would be the spearhead for this community to move forward? And I think you did a 2017 study on the research priorities,
Yes.
kind of. We have a whole society, at the foundation of the pyramid. However, the university and the SERC serving as a spearhead. So where and what research opportunities this spearhead of SERC is looking at in the coming 5 to 10 years?
So I would say that I'll use some of your language about infrastructure and then synthesis and analysis. The three broad areas where I think we will have a lot of focus in the coming years from a synthesis point of view will be on defining, architecting, modeling systems with increasing levels of cognition. There's a lot we know, but then there's a lot we don't know. How do we architect these systems? What are the right partitioning concepts? How do we even specify these systems? How do we test these systems? So I think that whole area of systems that have increasingly richer abilities to think and adapt will be an area of lots and lots of neat research in the coming few years. Second is, I would say, and of course I'm choosing one item from each. The second area is this area of analysis, where how do we analyze the systems that I just talked about synthesizing from the point of view of trust and resilience. And the third is infrastructure. For me, infrastructure is where we get into a framework that engineers in the future would use for both the synthesis activities and the analysis activities, which is what I think we're investing in today, which is the development of a set of methods to do design reasoning and design synthesis in computational space. So whether it's ontologies, semantic web technologies, that allow the engineers to do the synthesis and the analysis. I also think along with those three areas comes the whole area of education and human capital development, where I think we'll have to rethink within academia. I think we'll have to rethink how we teach, how we provide continuing education to continue to have the impact that we're having on industry and government. So I would say that those are the areas that we will likely focus on in the next 3 to 5 years.
So you mentioned this kind of how do we, for us as people in academics, so we're in the business of education, right? So how do we educate, all this future? So speaking of this, again, I think of your early book, this, all early research life cycle. How can that kind of life cycle management of a product that you worked before, how can we use some similar methods, thinking process to think about our education system?
We're doing quite a bit of that today. But I think of it as, so when our school was established in 2007, one of the phrases that certainly I use was the open academic model. And in my mind, an open academic model is a model that emphasizes the notion of porous boundaries. I think in order for us to have the impact we aspire to have as faculty members, we will need to invest in creating richer partnerships with industry and government. And while that is true in general, it is even more so in all systems related areas. Because so much of the knowledge discovery happens when you're actually working on complex systems. And for us to bring that insight back into the classroom for our students, for them to perhaps do research and then feed that back into the application domain, I think our ability to have impact through education will depend a lot on the kinds of partnerships we're able to build with industry and government, even more so in the future and even more so in the field of systems.
I do want to ask one question before we finish this up. So in your talk, and I think you mentioned that this discussion regarding principles versus rules, and I think you mentioned your PhD student even probably you wrote a paper on this. So I think this is really a very interesting and also a very important aspect of not only research but also in practice. So if you think of anything, a person can be a system. Your school is a system. University is a system, right? But all these, even though all these systems are so different in nature, however, I believe both principles and the rules apply easily to these things. So what did you find out from, of course I didn't read that paper. So what did you find out in that paper? What were your major conclusions, and what insights would you offer to me as a person when I look at principle versus rules?
Well, we use those concepts in life all the time. We just don't make them very explicit. So we have kids at home, and we try to convey certain values to them. And if we're able to convey values to them, we hope that when they deal with certain specific situations, their actions are consistent with those values. We can't teach them how to respond to every specific situation they'll come across in life, because that's not possible. And so you try to convey a certain set of values so that their actions in specific situations are consistent with those values.
Grow out of their value system.
That's right. I would say that one of our findings was that translating to a rules-based mentality when developing large complex systems too early can be detrimental to the development effort associated with that system. Too many rules. A very, very good friend of mine told me that if you have way too many requirements at the system level, that means you really don't know what the system should really do. You should have a very small number of well-defined principles, sacred expectations that ought to drive some of the lower level detail. Getting to too much detail too soon can be detrimental to the development of a system. But I'm happy to send the paper to you.
Yeah, I will look forward to it, because I think it's kind of even, you use example of educating kids, right? I think that's a very good example. It's really, and I also totally agree with you, if you have the rules too early and also too detailed, so that basically that kills creativity.
That's right. And I think there are analogs to that in systems that will be adaptive systems. Because you can't test every action, because you don't know what their actions will be. But you can test reasoning, hopefully.
That's right.
And so, yeah, I think those are the kinds of areas where I think we'll see quite a bit of exciting research in the coming years.
So just out of curiosity, when you're talking, I'm thinking, because early on you mentioned the word legacy system. So of course, we can reasonably assume that that legacy system was built, guided by the principles.
Yes, of the past.
Yes. Which do not necessarily apply.
That's right.
Nowadays.
May not apply.
May not apply, nowadays.
That's
So
right.
how do you work with a system that was designed and governed and operated with the principle that no longer, that is no longer valid?
Well, my contention is that often for legacy systems, we do not know what those principles are. If we knew what the principles were at the time that those systems were designed, we'd have a lot more respect for those systems than we do sometimes. I also think that every time we go about modernizing a legacy system, we will be much more effective in our efforts if we understood the rationale that the designers from the past had. The sad part is often that legacy system, the documentation associated with the legacy system that articulates that rationale doesn't exist or is not written down. can you imagine how powerful it would be if for some of the legacy systems we not only knew what the design is, but we also knew why the designers chose that path? What was the set of constraints those designers were dealing with? What were they thinking at the time they chose this option versus that? We don't have that design rationale captured in such a way that we have that insight into the legacy systems. If we did, I believe we would make much better decisions with how we evolve and modernize those systems.
So you're saying that basically, actually because of the lacking of understanding of those principles of the legacy system, sometimes actually probably the modern society people, we are probably doing something in a very kind of crude or kind of way that doesn't...
We are ignorant about what drove that design.
Yeah.
And I think it would cause us to certainly be much more sensitive to why a certain system is the way it is, and perhaps be more mindful when we think about how we want to evolve it. I also think that given that we realize this about systems that were built 30 years ago, we ought not to be making those same mistakes today for future generations. We ought to find a way to capture design rationale so that it will be there 30 years from now when people look back.
We should avoid, kind of the previous mistakes.
That's right.
My question would be, can we do that and how?
Well, that's one area of intense research interest to me. How do you capture knowledge, domain knowledge, in a way that makes it actionable? I happen to believe that the notion of design and architecture patterns represents a platform for us to do so, but it remains to be seen.
I think that's a very nice closing of our conversation. Thank you very much.
Thank you, Oliver.
Yeah.
Thank you for having me. Appreciate
Great.
it.
Yes.
Thank you.